98, yeah.
Which turns into what, 120% adjusted? That's nice. I feel like the room that's here now did pretty well on the quiz. So you guys aren't concerned. There must be some sort of relationship, right? There's something going on here. Oh, let's close. All right. So I did adjust the grades for the quiz. I explored a few different options, but what I decided to do was I standardized your scores, right? So I took the mean of our scores, the standard deviation, and I calculated your Z score, right? What? Using the stuff that the quiz was on? Blasphemy. And then I adjusted it to have a mean of 70%, which kind of historically for this quiz, it is a hard quiz. So I adjusted it to have a mean of 70% and a standard deviation of 30% to match the spread that we had. So kind of some trickery going on, but that's what I did. I'll make a note here. Grades for quiz number 2 are adjusted. And of course, I went through and checked all your kind of rounding and just the answers that you entered. I checked your written work. If I could find, I think there was, for example, there was a give me the Z score question, and a lot of people kind of took it that step further and gave me the probability instead. So then if I was able to find the Z score in your written work, then I gave you that mark, even though it's wrong, but you did it. So, and whenever I adjust something in the feedback, I'll say how many marks I added and why. There are more notes for me maybe, so if you have questions about that, then let me know. So for quiz number 2, are adjusted to have a mean of 70%. Maybe I shouldn't hand it back that written work. And a standard deviation of 30%. So there was quite a spread. I'll say the distribution of grades went from this to this. That's nice of me, right? Wow. All right. So in terms of the material from quiz 2, we can parking lot all of that, okay? That's not going to come back to haunt us until the final exam. And even then, we'll have more important things to focus on. So I'll give you a heads up on the questions to focus on, right? But that was kind of as bad as it gets, in my opinion. Okay. Today, we get to start what we're actually here for, and that is inference. Okay, so we're going to talk about kind of what is inference. And then today, what we're doing is we're just kind of laying the groundwork for the key tools that we'll need. And then for the rest of the week, we're going to introduce these general procedures that we use. And I know that's all vague and cryptic right now, but let's start here. And maybe that's not very nice. I'll remove that. So chapter 5. In the office, so I'm in that shared office, and we were just talking about how a lot of math courses, you have to cover all this kind of pointless, well, not pointless, but kind of all this stuff before you can get into the real course. And so now we've finally done that, and we're ready to do real things, real statistics. So chapter 5 is called Foundations for Inference. Now, inference is probably not something that you say every day, right? But inference is this, this field where we take sample information to learn about the population, or what we could say instead is we could say we take sample information to infer something about the population. Right? And so this is the meat and potatoes of statistics. In fact, I think at the beginning of the term, I started out and I said, okay, statistics is when we take sample information to learn about a population, right? So really inference is kind of the moneymaker of statistics, right? So we need inference for pretty much any field. And that's why you have to take this course or some version of statistics at some point, regardless of what you're studying. Okay, so let's talk about inference. So inference, instead of saying it's a real moneymaker, I'll say it's at the heart of statistics. That's kind of more touching, right? So inference is at the heart of statistics, which I'll put a little $sign next to it, because that's what it really means, right? That's why someone would pay you to work as a statistician, is to be able to learn about a population, right? Just using sample information, how can we learn about the population? Okay. And so really, it's when we take sample information to infer something about the population. Okay. And infer, it's not exactly right, but you could, in your mind, replace it with learn, right? So to learn something about the population, right? What does the population look like? Yeah. So what I want to do is kind of give us an idea for the next few chapters of what we're going to be doing, because it's nice to have this overview. Of course, it won't really make sense until we get through it, right? But it's nice to have this overview of, okay, what are all the things that we can talk about here? And so in chapter 5, I think of it as learning the rules of the road, right? In order to play a game, you have to learn the rules first. That's boring, right? But otherwise you can't play a game, right? And so it's kind of like, all right, how do we play this game? And then the rules are the same for every procedure that we're going to do. Just how we do it is going to change, but the rules are always going to be the same. Okay. So in chapter 5, which is what we're starting today, we learn the rules of the road, just kind of, all right, here in general, what are we going to be doing? Okay. We learn, I'll call it the rules of the road. But what I guess I should be calling it the rules of the game. That's cute. But rules of the road. Okay. So what we're building towards are, we're going to be building confidence intervals and doing hypothesis testing. Those things mean nothing to us right now, right? But those are the things that we're going to be able to do for each type of question that we come across. Okay? So we're going to be talking about things called confidence intervals and hypothesis testing. And it's totally fine. Those things don't mean anything right now. But like I said, I just want you to know where we're heading. Yeah. So we're gonna learn the rules for confidence intervals, learn the rules for hypothesis testing, and then it's kind of like The Sound of Music. When you know the notes to sing, you can sing most anything. Come on, guys, next time. Right? Okay, so I love Sound of Music. Anyways. Still don't understand how that's a Christmas movie. I know, right? That's weird. I used to watch it every time I visited my grandparents, which was a lot. It's a lot of Sound of Music to watch. Okay, so what are the different types of questions? Now let me just go to the index because that's going to be the easiest. So we're starting foundations for inference, and then we're going to talk about categorical data, right? Inference for categorical data, and then we talk about inference for numerical data, right? Going back to why is it so important that we know how to identify what type of variable we have, right? Well, it's because when I have to do my analyses, right, I need to know if I have a proportion, right? So if I have a categorical variable, I'll be analyzing the proportion. Whereas if I have a numerical variable, I'm going to be analyzing the mean or the means, potentially more than one. Okay. And so here, let's see here. Oh, wait, I don't need that. I don't need the page numbers. I just need this list. Okay. Get bigger there. So these are the different types of questions that we're going to learn how to deal with. Okay. This is a lot of what we're going to do in real life. There are others, right? But this is like, these are our bread and butter here. So these are the different question types. So in chapter 5, we introduce all these concepts using inference for a single proportion. Okay. So chapter 5 is basically 6.1, but in slow-mo, right? So we kind of go through it, we pick it apart, and then we kind of review it in 6.1, right? But basically chapter 5 is all of 6.1, just really, really slow. And then, so we start with a single proportion, and in terms of kind of what would that look like, right? A proportion, well, that could be what proportion of voters are going to vote for whatever candidate, right? Now I can't remember who we just voted in, but is it Tom Diaz? Diaz? I don't know. I guess Bazrin is out. That's the only one I remember. Catchy name for some reason. Anyways, right? So what proportion is going to vote for this candidate, right? That's one proportion. And so we can do inference for a single proportion. Or we could have two proportions, right? Maybe what proportion is going to vote, let's say Liberal in BC versus what proportion votes Liberal in Alberta, right? Is there a difference in those proportions? Probably, right? And so that's when we have a difference of two proportions. And then we can do goodness of fit using chi-squared. That doesn't mean anything, but really what we're saying is if we have more than 2 proportions, so what if we consider 3 or 4 or 5 provinces, or maybe all provinces, right? Then we can look at the proportion that vote Liberal across the provinces, right? Are they the same, right? Essentially the same, or are they going to be different? Yeah. And then we can expand it and we can say, okay, well, what if I have another variable that I want to introduce, and then I have a 2-way table, which is one categorical variable against another categorical variable. We can still test that with a chi-squared test. So that's where we're headed. So we start with 1 proportion, 2 proportions, 3 proportions, floor, no. Right? So we can look at any number of proportions. For numerical data, oh, cute. So here, you missed my singing. Maybe that's why you stayed out. It's like, oh no, this doesn't look good. For numerical data, we analyze the means, right? What's the average sales that I make off of this company, right? Is it less than 50,000? Is it more than 50,000? That kind of an idea, okay? And so then we have 1 sample means. There's a special case where the data is paired, right? And we'll talk about that. But spoiler alert, it turns into a 1 sample means question. Difference of 2 means. So now I have 2 different companies, each with their average sales. Are they significantly different, right? I tend to skip, and I'm going to make it kind of low key here, the power calculations. I'm going to gloss over it. It's not a full pen, it's a dotted pen. We're supposed to do it, but I skip it, and no one's caught me. So, and I think that's how life works. I'm pretty sure. You just don't get caught. So a difference of 2 means, and then if we have more than 2 means, then we use what we call an ANOVA. Okay? And so what we're going to learn is that we can do a confidence interval, and we can do hypothesis testing for any one of these different types of questions. So what we're going to be doing for the next little while is just every day we introduce a new question type, and we talk about how do I build a confidence interval? How do I do a hypothesis test for this question type? Okay. So, but first we have to do a little bit of legwork. Okay. Oh, and I should say, what's really, really nice is quiz 2, there's material from all over the place. Right? Quiz 3 is going to happen here, which is on chapters 5 and 6. But remember, chapter 5 is really just a very drawn out version of 6.1. So it's basically only on chapter 6. Okay? And so it's going to be really, really focused, and it's going to be all the different types of inference for categorical data. Okay? So that's going to be really nice, I hope. Okay. So how we do, or how we construct confidence intervals and how we do hypothesis testing will always follow the same procedure, okay, regardless of which of these question types we have. Okay. So how we construct a confidence interval or conduct a hypothesis test will always follow the same format, right? Regardless of what type of question we have. will always follow the same format, regardless of the type of question we have. I am putting quotes around the type of question, right? Because really what we're saying is what variable type we have, right? But I think it's easier to summarize it as the type of question. So as we move through these, right, you're gonna need to know, how do I know what type of question it is? And of course, I'm gonna tell you kind of the key things to look out for, right? Okay, now I have two proportions because, well, I have two sample proportions, for example, right? So it sounds breezy, right? Oh, it's just a confidence interval and it's just a hypothesis test. Even if we don't really know what that is, sounds easy, right? But there are a lot of nitpicky things that we need to keep track of, right? So just be aware. Okay. In terms of chapter 5, we're going to do 5.1 today, which is really just establishing a few things that we need, right? And some ideas that we need. And we don't really get to do anything, although I have an example that I want to end with. On Thursday, we're going to do confidence intervals for a proportion, so a one sample proportion type of question. One sample proportion type of question. So we'll start with confidence intervals, talk about that on Thursday, and then not nearly enough time on a 50-minute blip Friday class to talk about hypothesis testing, but it'll run into the Tuesday where I introduce 6.1. So don't worry. I know you weren't. I was. I looked at my own schedule and I was like, oh, what was I thinking? I think I wasn't paying attention. That's okay. Okay. 5.1. Point estimates and sampling variability. Point estimates and sampling variability. Okay. So what we're going to find is if we want to take sample information to learn about the population, which is ultimately where we're going, right? Then the sample information piece is going to be called a point estimate. Now we call it a point estimate just in general, because that can be applied to any one of these question types. So each question type is going to have its point estimate. So we can talk about point estimates in general, and then that'll lay out the framework. Yeah. For example, if I want to talk about a single proportion, so a single population proportion, I'm probably going to use a single sample proportion as my point estimate, right? That's going to be my best guess. If I want to talk about the difference of two proportions, for example, then I'm going to have two sample proportions and I'm going to look at the difference, and then that's going to be my point estimate. So depending on what type of question I have, that's going to determine what the point estimate is. But in this case, or I guess I should write that out first. A point estimate, because we use it quite a, or that terminology, we use it quite a bit. Okay. The point estimate is information from the sample that's going to serve as our best guess at what the population looks like. So it's information from a sample Remember, information from a sample is called a statistic. That will serve as our best guess for what the population looks like. For what, and maybe I'll say the corresponding population information. The corresponding population information. Fun to say, fun to do. Population information is a parameter, right? For what the corresponding population information, I'll say looks like, could say is, I guess. And so the point estimate is going to be that statistic, right? So a measurement from the sample, and it is going to have a corresponding parameter that we're trying to infer something about. Okay. All right. So let's, it was kind of early, so my creative juices weren't flowing. So I did a voting example kind of off the cuff, and I'm sick of Trump examples, so we're gonna go back to Obama. Phew. Doesn't matter who. And then just like I did now, I realized I had a missed opportunity. I should have used Hillary. Next time. I've already written it down. Let me make sure that I'm recording here. Yes, good. Obligatory freak out. Okay. Internal freak out. So if we wanted to predict a presidential election, right, that happens all the time, right? Who's predicted to win? How do we get that, right? How do we get these predictions? Well, statistics, of course. And so what would we do, right? If we're running this poll, I would take a random sample of American voters, right? And I would ask them, who are you going to vote for, right? And if you're like me, I just figure out who they want me to vote for and I just say that person. Works every time. Although not great for statistics, but that's okay. Right, and so what do? We take a random sample of the population that we're interested in, and then we can use that sample information to infer something about how the entire population is going to vote, right? You could, in theory, ask the entire population, how are you going to vote? And then you could know that, right? But that's going to be really expensive, probably too time consuming, and the election would be over, right? So there's that, and just very difficult in general. And so what's nice with statistics is we don't need to do that. We have these tools that we can use and say, okay, well, I can use a sample, that's fine. So to predict who will win a presidential election, Okay. We collect a random sample of 1,000 US adults, let's say. We have to specify they have to live in the States to vote for a president because we don't have presidents, and they have to be an adult in order to vote, right? And I mean, could ask if they even plan on voting, but let's just stick to US adults, right? Should be US voters maybe, but let's talk about just the adults. Everyone can vote, just don't. So we collect a random sample of, let's say, 1,000 US adults, okay? And what do we ask them? We ask them, who are they gonna vote for? And ask them who they will vote for. So, and let's say we find that 567 of those 1,000, right, say they're going to vote for Obama. And the only reason I'm avoiding Hillary is because I can't remember if it's 1 L or 2 L's. I know how to spell Obama. So we find that 567 people say they will vote for Obama. Yeah. So some of the things that we're going to keep track of are, what's our population? So when we're done, who can we generalize these results to? It's going to be just US adults, right? And so here, this is the population. So let's make a note here, right? Our results will only generalize to the population that we selected from, right? And so our results will only generalize to all US adults, right? The population. So that's something that you want to keep in mind, right? You can only generalize to the people that you selected from. Makes sense. But sometimes we get so caught up in it. Yeah. All right. So then the next thing we're going to keep track of is the sample size, right? And so here I took a random sample of 1,000. So my sample size is 1,000. And we found that 567 people said that they would vote for Obama. This is what we call the number of successes, right? If a success is someone saying they'll vote for Obama, right? In this case, it's all the information that we have. So here, usually how we denote it is with an X. X is 567, where X is the number of successes, which I know you're having flashbacks to the binomial, right? Because number of successes, we even used X as the number of successes in the binomial, right? The probability that X equals K was K successes, right? So we've already used it in that sense, but don't worry, That's about as far as it goes for us. Goes deeper, but it's okay. So what we have, right, is we can find a sample proportion of people who say they're going to vote for Obama, right? And so we can find 567 divided by 1,000. We'll call this the point estimate. Remembering that the point estimate is just shorthand for our best guess at how the population feels, right? So the point estimate for the proportion of US adults who plan to vote for Obama. Who plan to vote for Obama. So of course, 567 out of 1,000 is a proportion, and it's a sample proportion. And so now what we're gonna say is, do I have enough room to say it here? I'll put it on a fresh page here. The point estimate for a proportion, so a single proportion, is denoted by a p-hat. The point estimate for a proportion implies that it's a single proportion, right? Is denoted by p-hat. So it's a lowercase p with a hat on top. P-hat. And in case you're not reading the footnotes super carefully in the textbook, I do want you, does anyone remember pH fat? Come on. It's like a thing, I feel like it was in the 90s. I think it stood for, well, I was pretty young and I was under the impression that it was pretty hot and tempting, pH fat. So anyways, pronounced p-hat. And then the footnote says not to be confused with hat, the slang term used for something cool like this book. Cute. Anyways. No one remembers pH fat, huh? Okay. Like this book. All right, so p-hat. All right. So p-hat is going to be the notation that we use for a sample proportion. Yeah. The point estimate for a proportion, which is really saying that p-hat is the sample proportion. Which means that p-hat is going to be x over n, right? The number of successes over the sample size. The number of, and I don't know, I don't need quotes there, but the number of successes over the sample size. I think even if I just gave you this little blurb, right? 567 people out of 1,000 say they're going to vote for Obama. And I asked you, what is the sample proportion of people who say they'll vote for Obama? you would probably just do 567 over 1,000 in your kind of natural thinking, right? And so now we're just adding some notation here. So in this case, p hat is 567 over 1,000, which means p hat is 0.567. Remembering about proportions, proportions have to be between 0 and 1. So if you find yourself writing a proportion that's not between 0 and 1, something's gone wrong, right? And so let's just remember here. Proportions must be between 0 and 1. Okay. So this sample proportion, right, is our point estimate for the general US adult population. How do they feel like voting, right? So this is our best guess at what the population proportion is. Okay. So this is our best guess of what the population proportion is. What if we release this sample of 1,000 and I collected a new random sample of 1,000 and I found the sample proportion? Would we expect it to be exactly the same? No, right? We would expect it to be similar, right? Kind of in the same realm, right? We're randomly selecting. And so I expect it to be similar, but not exactly the same, right? And so then I release that 1,000 and I collect a new random sample of 1,000 and I find the sample proportion in that sample. Again, it's not going to be the same necessarily as the other two, but we expect them to be similar, right? So then in theory, if we go ahead and we do that tons and tons of times, then what we're going to find is we can build a histogram of all these sample proportions, right? And just by this miracle called the central limit theorem, it approaches a normal distribution, right? But let's just kind of jot that down before we lose it, before I lose it, right? And so we understand that if we collected a new random sample, right, the p hat would change slightly. Okay? So we understand that if we collected a new random sample, of 1,000 US adults. Oh, I keep wanting to capitalize adults. It's got a different vibe. Right. Our sample proportion would be slightly different. Bless you. Would be slightly different than p hat equal to 0.567. However, we expect all of these sample proportions to be hovering around what? Around the population proportion, right? Every time we collect a new sample, we say, this is my best guess at what the population proportion is, right? And then we get a new sample. Okay, now this is my best guess at what the population proportion is, right? And so what we're gonna have is we're going to have variability in these statistics. However, we expect all of our sample proportions to be close to the population proportion. To be close to the population proportion. Now, the population proportion, we're gonna need notation for that. And we're gonna use a lowercase p, even though population information, we typically denote by a Greek letter. So if you wanted to use pi, you can, but it gets confusing, right? Because pi is a constant and so we don't wanna get mixed up. Not that context wouldn't help us out, but just for simplicity, we just use a lowercase p. So here, this is gonna be denoted by p, or pi if you want, but I use p. And so does the textbook. In fact, I just usually do whatever the textbook is doing, right? So you're not, the only thing I'm holding steady on is my Q's, right? The textbook is really good about just writing 1 minus p all the time, but I'm lazy, so I use Q. I think that's healthy for you guys. Okay. It's like the one thing where I'm stubborn. No, I'm really stubborn, but in this scenario. I am a Taurus after all. Come by it honestly, I think. There. It's the only thing I know about star signs, astrological signs. I'm stubborn. So we're expecting all these sample proportions to, as we collect more and more of them, right, just in theory, and there is code in the textbook where they kind of recreate the scenario. You're welcome to look through it, but one of the problems that I have with that example is we have to assume that we know P, right? So in that case, then we're gonna say, okay, if we force P to be this, right? Then we can recreate all these samples and we can see that they're huddled around P, right? But the problem is that we're not gonna ever know P, right? Because what would that involve? That would mean I would have to collect information from the entire population, and then why would I be trying to guess at what the population looks like if I already have it, right? And so that makes no sense, and we don't need to do that, right? But let's just remember that we will never know P. We will never know P. Oops. But we use P hat as our best guess. Okay. So a group of people, I don't think it was a one-man job, although I'm not really sure who came up with the central limit theorem. Feels like a group effort. But the central limit theorem is basically how they arrived at it is through that simulation that they ran in the textbook, or that they have in the textbook. So here, I just want to show you guys. So here they're talking about a proportion of American adults who support the expansion of solar energy. And so here they're pretending to know the population proportion. And then they say, okay, well, one of the ways that we could figure out the sampling distribution of the p-hats, which is what we're talking about. I haven't called it that though, but it's too scary, right? Is we could run this simulation, right? So one of the ways that we could do that is through this simulation that they outline. And then there's some R code that you could recreate if you wanted to, right? And so I encourage you to do that. But like I said, one of the things I don't like is that we have to assume that we know P, and then we run all these simulations. So they take a random sample of 1,000, and how many times do they do it? I think 1,000 again. So although reading code on the fly is not that fun. And so we do this thousands and thousands and thousands of times. And then what's going to emerge is we get this normal distribution of p-hats, right? And so that's what, you know, they did way back when, before computers. So you can imagine how long that would take, but they did it. And now we can just use it as fact. Trying to decide if I put this on a fresh page or what. Fresh page is to summarize the variability, right? To summarize the variability of p-hat. What am I actually saying here? To summarize the variability of p-hat, what I'm referring to, bless you, is, well, every time that I, in theory, took a new sample, right, and calculated a new p-hat, the fact that they would be slightly different all the time, right, that is the variability of p-hat, right? Just that they would vary as we collected a new sample. Okay. But to summarize the variability of p-hat, we rely on the central limit theorem. Which, we abbreviate CLT usually. Central limit theorem is just as important as it sounds, right? Because the reason that we're able to build confidence intervals, the reasons we're able to do hypothesis testing is because of the central limit theorem. Otherwise, we wouldn't be able to do it. Now, just as a heads up, I checked my class list for Stat 240 and I saw a lot of names I know, so that's nice. In 240, we're gonna do it kind of the simulation way, which we can. Okay, but for now, kind of traditional statistics rely on the central limit theorem. Okay. And what better way to talk about it than to dissect this wordy thing. So what I want to do is just read through this blurb, and then I want to pick it apart, right? And say, and there's not enough room for me to kind of draw lines out of here, so I'm going to outline it below, okay? But we're going to pick this thing apart and really get to know it, okay? But first, let's read through it. So the central limit theorem and the success failure condition. Oh, another thing that sounds familiar from the binomial, right? What was I trying to do? I was trying to use the normal approximation to the binomial, but in order to do that, I had to check the success failure condition, and we still do, because when observations are independent and the sample size is sufficiently large, the sample proportion p hat will tend to follow a normal distribution, ta-da, with the following mean and standard error. Mean of p, which is the population proportion, and the standard error of p hat is the square root of pq over n. Okay. Like I said, we'll dissect that, but there we go. That looks familiar, right, from the binomial, right? We found the mean and we found the standard deviation, but now we're calling it the standard error, and that's because it's the standard error of a statistic. Okay. And I'll write that down, but let's finish the blurb first. So in order for the central limit theorem to hold, the sample size is typically considered sufficiently large when NP is greater than or equal to 10 and NQ is greater than or equal to 10, which is called the success failure condition. Good. First things first, the standard error is the standard deviation of a statistic, right? Before we were just talking about the distribution of single observations, right? But now I'm talking about the distribution of p hat. So now I call it the standard error instead, to emphasize that, hey, this is the spread for a statistic and not just an observation. Yeah. Okay. Maybe I'll just kind of do that. All right, so now let's pick this thing apart. So, or in other words, when observations are independent, okay, how do we know if they're independent? The thing that we're going to use when observations are independent, if the observations were randomly selected, right, then we can assume independence. If the observations were randomly selected, we can assume independence. So in order for our calculations to go ahead, right, first thing we have to do is were the observations randomly selected? Even if they weren't, right, if there's no mention of it in the question, although there usually is, right, even if there isn't, what would you have to do? You would have to say, I assume the sample was randomly selected, right? So therefore I can assume independence. We might not know, but those are the assumptions that we're working under. What about the next part? And the sample size is sufficiently large. And the sample size is sufficiently large and then it clarifies here, it's considered sufficiently large when if n times p is greater than or equal to 10 and n times q is greater than or equal to 10. where of course Q is 1 minus P. So this is what we call the success failure condition. Okay, what's the next part of this blurb? The sample proportion p hat will tend to follow a normal distribution with a mean of p and a standard error of root pq over n. Okay. The sample proportion p hat will follow a normal distribution I guess it says tend to, but that's okay. With mean p and standard error root pq over n. Which we can as p hat will follow a normal distribution with a mean of p and a standard error. But remember, the standard error is just a different name for the standard deviation if it's attached to a statistic like p hat. Okay. So then the standard deviation is pq over n. Sorry, the square root. We use the notation mu subscript p hat to denote that this is the mean for p hat is p, and the standard error of p hat is the root of pq over n. Just kind of reiterating. Okay, let's see if there's anything missing on here. So now we've got these all covered. In order for the central limit theorem to hold, the sample size is sufficiently large with the success failure condition. Okay, so we've picked apart this entire thing. And so that is the central limit theorem for proportions, or for one proportion. Okay. Of course, there's going to be a central limit theorem for each type of scenario, but I'm just going to introduce it to you, right? Give you the conditions, tell you the distribution, and then we go from there. Okay. But it's good to know the background of the central limit theorem. What's one problem? P, 1 minus P, 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 1 minus P. But I just said we're never going to know P. But we've got a good guess. So what do? We just swap out our P's for P hats because that's our best guess. Okay? And so we don't just do that, but for us, we do. So since we don't know P, we use our best guess at what it is, which is P hat. We use our best guess at what it is, P hat. So now, if we're going to just summarize these conditions, then if we rewrite these and just kind of rewrite the central limit theorem in terms of how we're actually going to apply it, right? So then our conditions / assumptions become, well, the first one is independence, which stays the same, right? Did I collect the sample randomly? Or here's where I assume, so here's where I state my assumptions. I assume it was collected randomly. It doesn't say, but I'm assuming it was. Okay. So independence stays the same. Was the sample randomly selected? Right. And I'll do a little follow-up here, or assume that it was. That can be the case. 2 is the success failure condition. Which says that I need to check if n times p hat, right? I'm swapping out p for p hat, has to be greater than or equal to 10, which means n is a sample size and p hat is a sample proportion of successes. And so this becomes, I need to have observed at least 10 successes. Let me just scoot this. Scoot. And on the flip side of that, NQ hat has to be greater than or equal to 10, which means I need to have observed at least 10 failures. So you didn't memorize it for naught, right? Now we apply it in a different scenario, but it is the same. Depending on how the question is laid out, right? Observing at least 10 successes, well, the number of successes we're denoting by X, right? So if you have X, X is just N times P hat, unless you've rounded P hat, right? So you could check, is X greater than or equal to 10 if you prefer, right? Sometimes we don't have that information. And the number of failures would be N minus X, right? Total sample, I take away my successes, the remainder are failures. So then, once these assumptions are checked, and I used to make you check the less than 10% condition, but I've dropped it. Only because the textbook gave me enough courage to. Right? They're like, oh yeah, it's rarely an issue, so we ignore it. Great. Less is more. Then we're going to say that p hat follows a normal distribution with a mean of p hat and a standard error of p hat q hat over n. And just to emphasize here, right? Since we don't know P, right, this is what we're going to use in its place. So since we don't have P, we use P hat as a point estimate. Knowing that it follows a normal distribution opens the door for finding probabilities, right? What's the probability of finding a sample proportion of 0.567 if it's actually less than 0.5, right, where Obama would lose, right? So an incorrect prediction, essentially, right? And so then we can attach probabilities to our statements, but we're not there yet, but we will. Okay, so the normal distribution is what is the gateway to finding probabilities. Okay. Which means this one?
Yeah.
Oh, X we're using as the number of successes. But you don't need to use X, it's just if you prefer to use X, because X is the number of successes, but if you take the sample size times P hat, it's also going to be the number of successes.
So X in the Obama case means 600 or 500.
Yeah, 567. I think I did 567, yeah. I know, so original. Right, so then 567 is the same as 1,000 times 0.567. Nice. Good. Okay. We won't do the entire question, but I do want to. Here they lay it out so nicely for you. Oh, come on. There. As soon as I hit the edge of the page, it wanted to go away. So what I want to do is just work through some questions, right? So I had my kind of made up example, but let's have a look at a different example. All right. And just gonna crop here. Okay, so as part of a quality control process for computer chips, an engineer at a factory randomly samples 212 chips during a week of production to test the current rate of chips with severe defects. You can see how that would actually happen, of course. How else would they keep track of, well, are our machines running properly, right? That kind of thing. She finds that 27 of the chips are defective. So we'll start with these little guys. Maybe I'll do dark. What population is under consideration in the data set? Good, but it's the chips during a week of production, right? Because the population is the thing that we can generalize to later, right? So the 212 chips come from the chips from this week of production, right? And it's important that we only generalize to that week, right? Because maybe 4 weeks ago, the machines were running fine, right? And maybe next week, maybe this week they're running fine, and then next week they're not running fine, right? And so we can only talk about the chips produced that week.
Are you framing that way also easily current rate of chips?
Probably. Yeah.
So you don't want to apply that across
during a week. And then, yeah, exactly. So then the current rate of the defects, right? So we're really focusing on just this week. Nice. The parameter that's being estimated, well, it sounds like we're going to be interested in knowing the proportion of defective chips, right? And so P is going to be the proportion of defective chips that week. Okay. What's the point estimate? Well, we only collected 212. I think it's safe to say that it sounds like they're producing a lot more than 212. And so the point estimate P hat is going to be X over N. which in this case is 27 divided by 212. And I find that my p hat is roughly 0.127358496. And with that, step away from the plate. We'll keep going on this example next day. If you have any questions, let me know. Feel free to try the rest of the example on your own. And I'll see you on Thursday. How
many decimal places is that?
Just as many as my calculator would give me.
Feels very rough.
Yeah, just approximately, you know. Oh. It's your work from quiz 1 and 2. I realized I didn't need to be hanging on to them.